In this video, we're going to talk about RMS, or root mean squared. Let's give a bit of a motivating example for why we actually care about the RMS value. Let's say that we're dealing with a sinusoidal input again. Now, if I were to ask you what the voltage is, you might have a little bit of difficulty. It's time varying. So the voltage at one time is going to be different from the voltage at another. You might say, well, then the voltage is Vm, the voltage is the magnitude. And I would agree with you. The only problem is that it actually turns out to be somewhat difficult to measure the magnitude. As a result, we need something else. So we might begin by saying, well, instead of it's just being the magnitude, maybe is it going to be the average? The idea of using an average is useful, but in this case, a pure average won't work, and let's see why. Here is a graph of my voltage. If you take a look, it's positive for exactly as much time as it's negative. So V average on its own would be 0. And that's not going to help me. However, let's take a look at the square. If I were to square V, what do I get? Well, it would come down and then jump up and then go back. So the first thing we notice is always greater than 0, which means the average would be non-zero, which is great. Now, how do you take the average of a function? In general, that's not an easy thing to do, but what we notice is this is periodic. And let's assume that it has a period t. If we do this, then what we might consider doing is summing up all the values and dividing by t. And that should give us a reasonable guess at the average voltage over one period. Now it is a function, so to sum it up we have to integrate. So v squared average is going to be 1 over t, the integral for one whole period from 0 to t, v squared, which is a function of t, dt. There's almost something very good here. We've solved for an average. This average will be greater than or equal to 0 always, depending on what v is. But it's the square of the voltage. It's not the voltage itself. We would need to take a square root then. So if I do that, I might say that VRMS, the root mean squared, is equal to the square root of that quantity there. Oh, my apologies. The square root of that quantity there, or the square root of V average. Now it's getting a little messy, so let's rewrite that. VRMS is the square root of 1 over the period, the integral over the whole period of v squared dt. Root mean square. This is also sometimes known as the effective voltage. And you'll see that in your textbook. Now, there's nothing special about doing this for voltage. I could have done it for current. Furthermore, there's nothing really special about the fact that v of t, when I was giving it to you, is a sinusoid. It could have been a square wave or a triangle wave. One important thing to know, though, and I'm going to not go through the derivation here, if v of t is a sinusoid, then VRMS turns out to be Vm over root 2. You can carry out the integration and see that for yourself. Sometimes I might just give you the phasor as follows. What does this mean? Well, I've given you a magnitude This means angle, and that's the phase. But the question you have to ask yourself, and always be careful, is this VM or VRMS? It doesn't really matter which one it is. Because we're dealing with phasors, and we know they're sinusoidal inputs, we can just multiply between the two. However, you just need to know which one it is. If I've given this to you as VRMS, then you might say, okay, then VM, the actual magnitude I need to turn this into a sinusoid, is root 2 times the magnitude 5. Therefore, as a sinusoid, V is root 2 times 5 is the magnitude. Cosine, omega t, now I haven't specified an omega, so we'll just leave it as omega, plus, because the phase is positive, 7 degrees. So this is just an alternate way of representing a phasor. Let's take a look at something. Why are we dealing with RMS in the first place? I'll give you a little bit of a hint of the answer. Let's consider a sinusoidal input, and what is the power delivered to a resistor? So what am I saying? Here is a voltage source, and it's sinusoidal, and there's a resistor. I'd like to know how much power, as a function of t, is being delivered to that resistor. Well, this is always true. It's v squared over r. On its own, this gives me a time-dependent answer. A reasonable question to ask, though, is, what is the average power? Well, we do know that P average is the same basic derivation, 1 over the period, integral from 0 to t, v squared over r dt. If r is a constant, I can take it out. So it all get us 1 over r times 1 over t, integral 0 to t, v squared dt. Remember this formula here. This is actually 1 over r times VRMS. So the average power delivered to the load under one period of its working is 1 over r times VRMS squared, or VRMS squared over r. So the RMS voltage just happens to appear in some of our equations. In this particular case, it was for the average power delivered to the load. We'll see in the next unit that we can use this to our advantage.